Good afternoon. I'm Harkirat and I'm going to be talking about my paper on video object segmentation titled Meta Learning Deep Visual Words for Fast Video Object Segmentation. This work has been done in collaboration with Mohammad Jafi, Anurag Arnab, and Professor Philip Durr. Our task is one shot video object segmentation. In this task, we are given the ground truth masks of multiple objects in the first frame, as can be seen in the images below, where the masks of rider and the bike are labeled. And the goal is to segment them in rest of the video as shown in the images on the right hand side. Thus the system needs to adapt to new objects and scene. Current approach for adapting is fine tuning. These methods take a pre-trained segmentation network and fine tune it on the first frame of the video for multiple iterations. Some of them generate hundreds of augmented images from the first frame and then fine tune on them. Some other methods perform online fine tuning as the video progresses to adapt better to post changes in the objects over the video. But there is a very big drawback of these fine tuning based approaches, that they are very slow. Thus, they are not useful for fast and online segmentation, which is a necessity in robots and autonomous agents, including autonomous cars. Some of the most accurate methods thus take about 15 seconds per frame because they use fine tuning. On the contrary, our aim is to make a method which can achieve fast adaptation to new objects and scenes. We make a method that number 1 needs no fine tuning at all, number 2 segments multiple objects in a single forward pass. Our method is based on metric learning. Metric learning is a technique which tries to embed similar instances close to each other. That is, embedding pixels from same object close to each other in a learned embedding space and embedding pixels from different objects far apart. Metric learning methods are mainly of two types: nearest neighbor based, which represent each class with an index of embeddings of all pixels, and prototype based, which represent each class with the mean of embeddings of all pixels. Although no one has tried prototype based methods for video object segmentation, we list here for completeness. Pixels in subsequent frames are classified with nearest neighbors in the nearest neighbor based methods, whereas in the prototype based methods, pixels in subsequent frames are classified with softmax over distances to each prototype. Nearest neighbors based methods have greater modeling capacity, whereas prototype based methods cannot represent complex multimodal distributions. But nearest neighbor based methods are computationally very expensive, whereas prototype based methods are simple and fast. The memory and time cost of lookup increases linearly for nearest neighbor based approaches. It stores redundant pixels, which is impractical for videos with massive numbers of pixels. Now let us try to analyze our problem. Here, our aim is fast adaptation, but the main challenge is that the object distribution is complex. This is because the object may be observed in different configurations. Prototype based approach cannot handle such complex distribution, and nearest neighbor based approach is slow. We propose to represent object as a set of cluster centroids in a learned embedding space or visual words which correspond to object parts in image space as are shown in the bottom row in the figure. The TSN plot in the middle shows how different object parts cluster in different regions of the embedding space, and thus how our representation captures the multimodal distribution of pixels constituting an object. The use of visual words enables more robust matching, as can be seen in the top row, because although an object as a whole may be subject to occlusions, deformations, viewpoint changes, or disappearing and reappearing, the appearance of some of its more local parts may stay consistent. But doing this is not straightforward because ground truth labels are not available for object parts, and the ground truth labels for assignment of pixels to object parts are also not available. Let us see how we deal with this problem. Now we show an overview of the proposed method. The first frame of the video, or the reference frame, which forms the support set S in our meta-learning setup, passes through a deep segmentation network F to compute a d-dimensional embedding for each pixel. A dictionary of visual words is then learned by clustering these embeddings for each object in the reference frame. Now, a query frame passes through a deep segmentation network f of theta to compute a d-dimensional embedding for each pixel. Pixels of the query frame are classified as one of the objects based on their similarities to the visual words. The model is meta-trained by alternating the learning of visual words given model parameters and the learning of model parameters given the visual words. Now we see how video object segmentation is a meta-learning problem. Meta-learning is defined as learning from a number of tasks in the training set to become better at learning a new task in the test set. In the context of video object segmentation, the task is to learn from ground truth masks of the objects in the first frame of the video, which is the support set, to segment and track them in the rest of the video, which is the query set. And each video presents a new task, which can be seen in this video. We have many such tasks in the training set, and all of them together compose the meta train set. Similarly, we have the meta test set, which comprises of the videos in the test set. The objects of interest from the first frame often change and transform. As a result, adapting the model throughout the video is vital to achieve good performance. We adapt a model by simply updating the set of visual words that represent the object. And now the matching will be done to the new visual words. None of the existing visual words are discarded because each object may revert to its original shape and appearance during a video sequence. In this image, it can be seen that as the object pose changes over time, newer visual words, which are denoted by gray and light blue colors, are learned and added to the dictionary of visual words. In this video, we show a qualitative comparison of our method to our GMP, which is the state-of-the-art method in Davis 2017. So in terms of results, we first evaluated on Davis 16. You can see that we are the most accurate amongst all fast methods, that is, methods which don't use fine-tuning. And we are more than 100 times faster than fine-tuning based methods while still maintaining good accuracy. Similar trends are observed on Davis 2017 validation dataset. It can again be seen that our method is state of the art in terms of accuracy. This graph shows the comparison of speed and accuracy on Davis 2017 dataset. Entries on the Pareto front, that is, no other method is both faster and more accurate, are marked by a star. The speed is on a logarithmic scale. It can be seen that our method lies on the Pareto front. This figure shows that increasing the size of the visual word dictionary improves the representation of the object and thus improves segmentation outputs. This is because it can capture the intra-object variance. For example, the lost face of the human in yellow in the first row, the lost tail of the dog in the third row, and the missing legs of the horse have been recovered in the last column because of this property. This table shows comparison of other metric learning based approaches. It can be seen that we are much more accurate than prototype and nearest neighbor based approaches and still very fast. This shows the effect of visual word dictionary size, hyperparameter on an algorithm's accuracy, runtime, and memory consumption. The accuracy starts saturating around k equal to 50. However, the runtime and memory increase linearly with the number of clusters. As a result, we use k equal to 50, which provides a good balance between accuracy and speed. In conclusion, we propose an alternative of fine tuning for efficient adaptation, which is based on an efficient object representation. Questions?